scientists achieve nuclear fusion breakthrough with a blast of 192 lasers. The advancement by Lawrence Livermore National Laboratory researchers will be built on to further develop fusion energy research. Scientists studying fusion energy at Lawrence Livermore National Laboratory in California announced on Tuesday that they had crossed a long-awaited milestone in reproducing the power of the sun in a laboratory. That sparked public excitement as scientists have for decades talked about how fusion, the nuclear reaction that makes stars shine, could provide a future source of bountiful energy. The result, announced on Tuesday, is the first fusion reaction in a laboratory setting that actually produced more energy than it took to start the reaction. This is such a wonderful example of a possibility realized, a scientific milestone achieved, and a road ahead to the possibilities of clean energy, Arati Prabhakar, the White House science advisor, said during a news conference on Tuesday morning at the Department of Energy's headquarters in Washington, D.C. An even deeper understanding of the scientific principles that are applied here. If fusion can be deployed on a large scale, it would offer an energy source devoid of the pollution and greenhouse gases caused by the burning of fossil fuels and the dangerous long-lived radioactive waste created by current nuclear power plants, which use the splitting of uranium to produce energy. Within the sun and stars, fusion continually combines hydrogen atoms into helium, producing sunlight and warmth that bathes the planets. In experimental reactors and laser labs on Earth, fusion lives up to its reputation as a very clean energy source. There was always a nagging caveat, however. In all of the efforts by scientists to control the unruly power of fusion, their experiments consumed more energy than the fusion reactions generated. That changed at 1:03 a.m. on December 5th when 192 giant lasers at the laboratory's National Ignition Facility blasted a small cylinder about the size of a pencil eraser that contained a frozen nubbin of hydrogen encased in diamond. The laser beams entered at the top and bottom of the cylinder, vaporizing it. That generated an inward onslaught of X-rays that compresses a BB-sized fuel pellet of deuterium and tritium, the heavier forms of hydrogen. In a brief moment lasting less than 100 trillionths of a second, 2.15 megajoules of energy, roughly the equivalent of a pound of TNT, bombarded the hydrogen pellet. Outflowed a flood of neutron particles, the product of fusion, which carried about 3 megajoules of energy, a factor of 1.5 in energy gain. This crossed the threshold that laser fusion scientists call ignition, the dividing line where the energy generated by the fusion equals the energy of the incoming lasers that start the reaction. You see one diagnostic and think maybe that's not real. And then you start to see more and more diagnostics rolling in, pointing to the same thing, said Annie Critcher, a physicist at Livermore, who described reviewing the data after the experiment. It's a great feeling. The successful experiment finally delivers the ignition goal that was promised when construction of the National Ignition Facility started in 1997. When operations began in 2009, however, the facility hardly generated any fusion at all, an embarrassing disappointment after $3.5 billion investment from the federal government. In 2014, Livermore scientists finally reported some success, but the energy produced was minuscule, the equivalent of what a 60-watt light bulb consumes in 5 minutes. Progress over the next few years was slight and small. Then, in August last year, the facility produced a much larger burst of energy, 70% as much energy as the laser light energy. In an interview, Mark Herman, program director for weapons, physics, and design at Livermore, said the researchers then performed a series of experiments to better understand the surprising August success. And they worked to bump up the energy of lasers by almost 10% and improve the design of the hydrogen targets. The first laser shot at 2.05 megajoules was performed in September, and that first try produced 1.2 megajoules of fusion energy. Moreover, analysis showed that the spherical pellet of hydrogen was not squeezed evenly, and some of the hydrogen essentially squirted out of the side and did not reach fusion temperatures. Scientists made adjustments that they believe would work better. The prediction ahead of the shot was that it could go up a factor of 2, Dr. Herman said. In fact, it went up a little more than that. The main purpose of the National Ignition Facility is to conduct experiments to help the United States maintain its nuclear weapons. That makes the immediate implications for producing energy tentative. Fusion would be essentially an emissions-free source of power, and it would help reduce the need for power plants burning coal and natural gas, which pump billions of tons of planet-warming carbon dioxide into the atmosphere each year. But it will take quite a while before fusion becomes available on a widespread practical scale, if ever. Probably decades, Kimberly S. Boodle, the director of Lawrence Livermore, said during the Tuesday news conference. Not 6 decades, I don't think. I think not 5 decades, which is what we used to say. I think it's moving into the foreground, and probably with concerted effort and investment. A few decades of research on the underlying technologies could put us in a position to build a power plant. Most climate scientists and policymakers say that to achieve that goal of limiting warming to 2 degrees Celsius, or the even more ambitious target of 1.5 degrees Celsius of warming, the world must reach net zero emissions by 2050. Fusion efforts to date have primarily used donut-shaped reactors known as tokamaks. Within the reactors, hydrogen gas is heated to temperatures hot enough that the electrons are stripped away from the hydrogen nuclei, creating what is known as plasma. Clouds of positively charged nuclei and negatively charged electrons. Magnetic fields trap the plasma within the donut shape, and the nuclei fuse together, releasing energy in the form of neutrons flying outward. Thank you very much for watching our video. If you enjoyed the video, give it a like. And if you want more interesting videos like this, don't hesitate to subscribe to our channel and hit the bell icon.